Are you looking at use salt question 7? Have I got that up right? Okay, so I'm in the right place. We're going to do chapter 8.2 today. And chapter 8.2 is a continuation of hypothesis testing. In fact, there's going to be 4 sections, 8.2, 8.3, 8.4, I think they're called. This time, we're going to look at hypothesis testing of means when the sigma is unknown. So it's this guy. This is much more realistic than 8.1. In 8.1, it was very number intensive. You had to do a lot yourself. In 8.2, most of what you need to do is going to be done using SALT. You still have things to do, and the structure's the same, but kind of the approach is going to be a little bit easier because of a lot of the heavy lifting has been done by the software. So a lot of the calculations are going to be done for you. And you just, basically, you need to know how to put the information in. So a hypothesis test to do with means, but sigma is unknown. You're going to get in these questions basically this stuff here. There's going to be a story, and in that story, you're going to be told what the mean of the sample is, what the standard deviation of the sample is, how many items are in the sample. Like the sample was 200 people, a significance level to compare your hypothesis against, and some story, an alternate hypothesis. And this some story is a statement that you're trying to find evidence to prove it's true. And each one of these boils down into the same 3 combinations that you've always had. You get, is there enough evidence to prove that the mean is bigger than 50? This second one, is there enough evidence to prove that the mean is less than 90? And this last one, is there enough evidence to prove that the mean is different, in that case, to 13? So let me show you my own example of one of these types of questions. And we're going to go through the list, the kind of the way that you would do it. And we're going to let SALT do most of it for us. So a zoologist believes that the average weight of a new species of bat is over 5 pounds. That is essentially, you've been told HA. You want to prove, is this true, right? Are the average weight of these new bats, is it more than 5 pounds? Can I prove that? So he tests a hypothesis. He collects a sample of 12 bats, which is not very many. And the average weight of these bats is a little bit more than 5 pounds, 5.6 pounds, which he's happy about, right? That's sort of evidence. And the standard deviation of this sample is 0.6. I think in every question you're going to get, the mean and standard deviation and the number are going to be told to you in the story. You don't even need to calculate them, with the exception of one question where you had to do it. So here is the last of the question. Is there enough evidence to show that the average weight of these bats is over 5 pounds using a significance level of 0.05, right? So that's the story. So we are going to look at that. And the first thing we're going to do is from that story, we're going to collect all the data that we need. So we need to know the mean. Well, in that story, the mean was 5.6 pounds. We need to know the sample standard deviation, which in this case was 0.6 pounds. So far, so good. We need to know N, the sample size. In this case, he was doing 12, which, by the way, means that the degrees of freedom are 11. And what else do we need? We need a significance level, and that is 0.05. That's very like 8.1, isn't it? It's the same kind of things that you collect in 8.1. The only major difference is in 8.1, won't that be sigma rather than the sample standard deviation? It'll be sigma, the population standard deviation. Okay. Now, once we've collected the data, let's start by setting up our null and alternate hypothesis. Our alternate hypothesis is there enough evidence to show that the average weight is over 5 pounds? Average weight of population bigger than 5. Right, that comes from here. The null hypothesis is the same number, right, but equal 5. And that's exactly what happened in 8.1. So far, so good. Now, the second step is find the p-value. Well, if that was example 1, this would be like 10 minutes of number crunching and button pressing on our calculators, and eventually we would get it. But it's now going to be a lot easier. So I'm going to show you how we can do this using SALT. So here is a question, and don't worry about it. We're going to do mine. So we hit use SALT, and when you do that, this guy appears, right? This is the main page to SALT. Now, what you're going to do is, because who knows where it was last time, you're going to hit this one here. It's called inferential statistics. I'll try and make it maybe a bit bigger. There, can you see it now? Inferential statistics. That's the place that you're going to go to. Now, in the procedure, if you click on this, there's a whole load of choices, but the one we're going to do is one sample t-test. Whenever sigma is unknown, it's a t-test. In 8.1, sigma was known, it was a z-score test, right? Now it's unknown, it's a t-score. So make sure that says t-score. The sample mean was 5.6. The standard deviation was 0.6. And the sample size in this story was 12. Do you see how these numbers came from what I'd already written down? Right. Then you go down here, and this is a bit annoying, but we'll live with it. The hypothesis test. It was bigger than 5, right? So you put 5 and you do greater than. Now, I've already complained about this to the other class, but I still want to get out of my system. To me, wouldn't it make better sense if you switched the location of these two things so that it would say greater than and then 5 instead of 5 greater than? It just sounds bad, doesn't it? But can you see that's greater than 5 when you put them together? We're good? Now, once you put all the information in, you hit generate results. And here are all sorts of things, but the only one that really matters is the p-value. So we have got what would have taken us 10 minutes to do last time. We can just write it down. It's 0.00267. And do you know at the top, they've got my little null and alternate hypothesis written as well. Are we okay with what I've just done? Any questions you ask? Okay, so I'm now going to return back to what this looks like. And we've just found the p-value. It's great, like that. So what's the third step going to be? We're now going to go straight into the test. And the test is always the same. Is the p-value less than the significance level is 0.002647. Is that less than 5%? And if you look, that's quite clearly smaller, isn't it? This is a tiny number. And so when the answer is yes, we've basically solved the problem. And what we've got is a significant result. Which means we can reject H naught. In English, we would say something like this. The average weight of bats is greater than 5 pounds. So we would say it's a significant result that we found a significant result that the average weight of bats is greater than 5 pounds. So we've actually proved what we're hoping to prove, that this new species of bat do weigh on average about 5 pounds, more than 5 pounds. Suppose this p-value wasn't a tiny number, suppose it was 0.22, then the answer here would be no. And when it's no, it's not a significant result, so you don't reject H naught. And it's not significant, right? We have not proved this. It may be true, it may not, but we haven't proved that it is. Are we comfortable with the process? Right, so what I'm now going to do is show you the slight idiosyncrasies that the textbook has. And how you're going to do your answer. To give you an example, see how I got this p-value? Wouldn't it be really nice if they just had a box and you typed the number in? You know, that's how WebAssign should do it. That's not what WebAssign does. What they do is they give you things like this. And they give you a list, and you pick the one that belongs inside. So this one here might be less than 0.01. Yeah? So that's one of its little idiosyncrasies. But hopefully it won't cause too much trouble. Right, so let's see what that looks like. I can move this back here, right? Close that off. Right. And here's our first story, question 7. So I'm going to add a few other things as we go through this. What we're doing in 8.2 is a student T distribution, right? Instead of a normal distribution, which is 8.1 as Z-score, we're going to do a student T distribution, right? 8.2. Is it appropriate to use it? And the answer is yes. Why? The distribution is mound-shaped and symmetric, and sigma is unknown. As long as you know that the data is roughly a single hill, right? Symmetric mound-shaped, you're allowed to use this technique. If you've got data that's all over the place, right? You know, 2 hills skewed to the left, then you shouldn't be doing this test anyway, right? The question should be, no, I'm not doing it, the data doesn't fit. So that answer is pretty much going to be the same answer every time. So if you just remember that one, you'll do them all. Yeah. A random sample of 25 values had a mean of 12 and a standard deviation of 2, and use a level of significance of this guy to conduct a two-tailed test. The claim that the population mean is 11.5. Okay, so since this has 25 numbers in it, the degrees of freedom is n take away 1, 25 take away 1. So the answer you would write down there would be 24. Now, we're being asked to conduct a test to claim that the population mean is equal to that one. Right, let's go through each one and throw it out for a different reason. I'm kicking out the first one because H naught never has a greater than or less than in it. I'm kicking out that one because it never has a greater than or less than. So that means it's either number 2, 4, or 5. Now, out of these three, the one that we're comparing is equal, not equal. So it's that one. Now it asks us here, you get a t-value, a funny p-value, and a conclusion. So let's show you how that works. In this story, I'm going to have to write it down because this picture's going to disappear in a minute. We know that n is 25. We know that the mean is 12, that the standard deviation is 2, and we're going to test that it's not 11.5. So here it goes. Use salt. Go in here. The sample mean was 12. Its standard deviation was 2. The sample size was 25. We want to test that it's not 11.5, right? Equal, not equal, that's a split, right? It's equal to or it's not equal to. So we got this fella. Now, if I generate the results, there's a whole load of numbers. In this question, they wanted the t statistic, which is 1.25, and they wanted the p-value, which is 0.223351. So if you can imagine those numbers, I've written them down, but I'm going to use the numbers that we just said and fill in the spaces where they belong. Compute the t statistic to 3 decimal places. In this case, it's 1.25. That's as good as you can get. Now, the p-value was 0.22. .22 makes it that one, right? Would you agree 0.22 is somewhere between here and here? And do we reject or fail to reject? We fail to reject, don't we? So it's that one. That means there's not significant evidence. So for the most part, your homework is going to be picking the right dot, occasionally writing in some numbers, but most of the time just picking the correct answer from a choice of 2 or 4. Anything in that you want me to talk about before I move on to the next question? Okay. I'm going to do the next question on paper, but it's going to be from the homework. I'm just going to kind of read the story, and as I go through it, I'm going to collect all the information that we kind of require, which is basically this, right? So this one is question 8, or at least it's going to be a version of question 8. And in this story, a new drug for arthritis has been developed. However, it's thought that the drug may change your blood pH. So a random sample of 36 people. Right, random sample of 36. Boom. Blood test shows that the mean of this sample was 8.6. That's its average pH. That the standard deviation of the sample was 2.9. That the significance level that we should use is 5%. And we're being asked to use a 5% level of significance, right, to test the claim that the drug has changed the way the pH level of the blood is. And they told us that normal blood has a pH of 7.4. Right, so I got everything I need to get this set up. So I need to figure out who these two guys are. Now, the story was, is there enough evidence to prove that it had changed it? So it's another one of those equal to, not equal to's. Okay. Is there enough evidence to prove that the new drug, right, which did this, has it changed that? Now, when I look at that, I can say, I can tell you better than that. Isn't there a lot of evidence to prove that it's bigger, right? The pH has increased. But the question said only that it's different, right? So you go by what you're being asked to prove, not what you think would be easier to prove. So I'm now going to go into WebAssign, in particular into SALT, and there's question 8. So what is the level of significance? 0.05. They kind of ask you the same group of questions. So after a couple of questions, you'll get used to it. Now, one of these 5 dots is the same guy that I just wrote in. And the one that we're going to pick is the equal, not equal to one, right? Which is the top one. Can we do this? Well, yes, we can. I'm choosing that one. Now, they want us to get the value of the sample statistic. That is them wanting you to tell me what the T number is. And then what p-value. So time to start putting the numbers in. So I know that the mean of the sample was 8.6. I know that the standard deviation was 2.9. In this case, the sample was a sample of 36. We are comparing it, is it not equal to 7.4? So not equal to 7.4. Right, when I hit that, I should get the numbers I need. And they wanted 2 numbers. They wanted the T, which is what? About 2.48. And they wanted the p-value, which is 0.0179. So when I go back into here, I should be able to type in the T, which is 2.48. And I wish I could just type in the p-value, but instead I'm going to have to pick one of these. And the p-value that we got was 0.0178. 0.01, not that one, 0.01. That one. Sorry. There, that one. 0.017 lies in this range. Now, here's a little picture of what does that look like. Well, if I brought back the thing, you would find out that the guy you're looking at is this one. Now, is a p-value of 0.0179, is that less than 0.05? And the answer is no, it's not. And when it's no or not, not insufficient evidence is your pick, and it's not that one. So you pick the two that mention not statistically significant, and from the two up here that mention it, you've got this one and this one. Oops, I'm glad I checked. You always pick the fail to reject. When it's not statistically significant, you pick the one that says we fail to reject. Those two always go together. Are we good on that one? Right. Let's do one on my own. Just mix and match. Suppose we collected some data and I wanted to prove the average cost of gas in Bremerton is more than, God, now I'm going to have to try and be realistic. What's the going rate for gas? What would you, if you went out right now and just the first one you've seen, what kind of number would you get? Anybody want to help us out here? What's gas costs?
It's around $2.75 a gallon.
Okay, so let's suppose is there enough evidence to prove that the average cost of gas is more than 2.60, right? So how would we prove that in Bremerton, at least, the average was more than that? Well, I would go out and I'd find 20 gas stations. Now I'd just drive about until I'd seen 20, right? It's pretty random. And I'd find out what the average price was. And let's just say it was $2.75, like Chris said. And I'd get the standard deviation. And you know, if you've got 20 numbers, you can always get the mean and standard deviation using your calculator also. And let's say that the standard deviation was 15 cents. And I am going to use a significance level of that guy. Okay, so I need an H naught and I need an HA. In this case, is it more than 260? Equals 260. Right. Once you got this, you're ready for solve. So I'll close this fella off and I'll go in and see how this works. Oops. I think I may have chosen the wrong window. Try that again. That's better. Okay, who should we pick? Who should we pick? There, I'll use this one. I just need the button. Click on it. It's going to be same old, right? Once you've done 3 or 4, this should become second nature. The sample mean was $2.75. The standard deviation ended up being 0.15. The number of places I looked was 20. I want to know if this is evidence that it's greater than 260. So you see, that's what the filled in table looks like, right? Sample mean, standard deviation, how many numbers, bigger than 260. Generate the results. If they wanted to know what the t statistic is, it's this guy. What does that look like as a p-value? The number is so small that they're telling you that the answer is essentially 0. Would you agree less than 0.00001, right? Which would mean that it's significant and that we've managed to prove that the average cost of gas in Bremerton is in fact more than 260. Are we good? Any questions? Right, let's look at, let's return now, jump around as I can, and do one of these questions. What one do I want to do? Let's do the coyote one. This is question 9, since it's in front of us. There is 41 coyotes in a place in northern Minnesota. The average age of these animals is only 2.07, so just over 2 years. The standard deviation of their age is 0.84. All of those things, I've written them down. Now, significance level is 0.01, and somewhere in there, there's a sentence, and the sentence that we're after is that one. Does the data indicate that coyotes in this region tend to live longer than 1.75? Longer, right? More, so mu greater than 1.75, and the other one is equal to 1.75. So let me show you what I've just written down from that story before we return back to Sol. See all the numbers in that? If you've got this, you are ready to go, right? You can do any question. It's pretty much handed to you on a plate now if you have those numbers. So I'm now going to return back to that guy. And we'll use Sol. And the mean is 2.07. That the standard deviation was 0.84. And the sample size was 41. And we wanted to prove, is it bigger than 1.75, right? 1.75, was it bigger? Are you happy about how those numbers fitted from what I had in paper, where each one goes? So when I hit generate results, we should be looking at it. And the T statistic, because I know they're probably going to ask me for that number, is 2.439. And the p-value is 0.009623. So significance level, 0.01, check. Which one of these has the greater than guy? That one. Student T. What's the test statistic? That is the T, 2.439. What is the p-value? Well, it's 0.009. 0.009. It's that one. Right? 0.009 belongs there. Do a sketch of it. It's tiny. Is this significant at that level? And the answer, yes, it is. And you reject a no. And it's significant. And we're finished. Usual, just in case. Any questions? We need a joke, don't we? Okay, you're about to get one. Oh, Bailey's all in favour of my jokes. I like Bailey. Right.
Well, I was wondering one thing, like,
Uh-huh.
so if you're driving around sampling gas stations,
Yes.
wouldn't the gas expenditure be a factor in that?
No. You assume that the outside factors don't count, only the price at the station is. What you should be careful about is that you get a good random sample. Because I've seen this. Do you know that if you have a gas station that is in a popular through area, there's a good chance, not all of them, isn't a good chance that the gas is relatively expensive. And then the most expensive ones are the out of the way places. See if you find a garage that's like nothing near it, you know, it's only 1 in 5 miles, don't they tend to be even more expensive, right? So gas varies a lot in price. So if you want to do a random sample, you really should be taking, you know, a gas station that's kind of on its own, a gas station in Warren Way, you know, a gas station just before you're about to go onto the motorway, you know, different kinds of, you know, places to give you a kind of big picture of what it's like. If I just drove around, it might not be too random because, you know, it depends where I live, right? I might live in a place where the gas is quite cheap, and then you go over to Silverdale and it's, you know, 5 cents dearer, more cheaper. Okay, oh, the joke, that's right. I may have told you this one. What do you do if you get attacked by a group of circus performers? Don't know? You go for the juggler first. Juggler? Juggler? Oh, God, it's bad if I have to describe it. Okay.
All right, stop clowning around.
Why don't sharks eat clowns? They taste funny. Okay, has anybody got a corny joke before we continue with this?
My son, he has this knock knock joke he uses on a lot of people. You probably heard it, but
It's fine, go for it.
all right. Knock knock.
Who's there?
Interrupting cow.
Interrupting cow who? Oh, that one.
Yeah.
Okay, knock knock.
Who's there?
Doctor.
Doctor Who.
How did you guess? That one only works if you know the sci-fi show Doctor Who. Who have we? Courtney, do you have a joke for us? She may be on chat. Have you got a joke for us, Courtney? Last chance. Anybody else get another joke before we move on then?
Yeah, I have a joke.
Go for it, Chris.
What happens when you collect a lot of data trying to disprove observation bias?
God, that sounds a very clever joke. I don't know. What do you call it?
The results are exactly what you expected.
Oh, that's bad. That is bad, Chris. You should be embarrassed to even repeat that joke. But considering how bad my jokes are, I don't really think I can fault you too much. Okay, I'm trying to find one example, and for the life of me, I now can't find it, where you had to calculate the mean and standard deviation first before you could do. I think I found it. Come back. Okay, why did Darth Vader go to the music store? You don't know? To find the hidden rebel bass. Or bass.
AT.
Okay. I found this darn question, and during all my nonsense, I've gone and missed it again. Found it again. Okay, of course, it would have to be unlucky 13. So let's show you question 13. Here we have a set of data and a story connected to it, and I'm going to try and set up the key numbers that we always want. So although you can't see, I'm writing down X bar, the mean of the sample, S, N, and alpha, right? So in this story, let X be the random variable that represents red blood cell count, RBC, in millions of cells per cubic millimeter of whole blood. The X is distributed approximately normal for the population of healthy female adults. That's just telling us it's okay to do the T thing. Suppose that the mean of this is 4.76. Suppose then you take a female patient, and this person, you took 6 blood tests. So that 4.76 is what the typical average for a healthy person is. In other words, they've just told me that mu is 4.76. Unfortunately, this is my data. Now you can see there's 6 numbers, but I don't know the mean and I don't know the standard deviation. So how am I going to get that? Well, I'm going to hit use salt. And when you hit it, do you see that it has already got the numbers ready to use them? Can anybody remember where along the top I'm going to get the mean and standard deviation of these 6 numbers? One of these guys. Can anybody remember which one it was? Number 2, that one. Yeah. So the mean is 4.4. The standard deviation is 0.2826. And there were 6 of them. And that is how you get those missing numbers. So you go here and you type in 4.4, the mean. You go here and you type in the standard deviation of 0. To 2 decimal places, so 0.28. Now, do the given data indicate the population mean is lower than that guy with that significance level? So that is 0.05, and we need to prove, is it lower than 4.76? So I'm going to have to leave this for a second, and then we'll come right back to it. There's all the data. Lower than that. Is there enough evidence to prove that it's lower than this number? Lower than 4.76. Or equal to 4.76, right? So there is all the data. Now it's just like every other question. So when I, oops, get somebody in chat. Okay, you got it. Basic, and this guy. So I'm going to go here. I'm going to use salt again. I'm going to use it to find the p-value. Now, if you look along the top, you go to here, inferential statistics, click. And you see it's all set up for us. The only thing that's not is it less than 4.76? So is it less? Is there evidence to prove it's less than 4.76? Generate result. And I'll write this number down. The t statistic is negative 3.12, and the p-value is 0.0131. So back to this question, significance level was 0.05. The less than is that one. That one's standard answer. The t statistic is 4.76. The p-value that we got is 0.0131, 0.01311. Is that one? Is that right? No. There we go. Got my digits mixed up. 0.0131 is between here and here. There's my picture. Oops, wrong one. There's my picture. Is this statistically significant at the 0.05 level? Yes, it is. It's less than it, so it's statistically significant. And the usual two choices that mean statistically significant. Is that, have we got a flow now to these questions? Pretty much each one in the storyline has all the numbers you need, and then you go to salt and you find the p-value. And if it's small enough, that means less than alpha, statistically significant, you've got the evidence you want. If the p-value is too big, you don't have the evidence. It's not statistically significant. So
For the homework on question 5, I believe, or 6, for a student's t distribution with BF10 and t, it gives you those two numbers. It says consider the following, and it has us use salt to enter those two numbers. Can you go over that?
what number is that?
I believe it's number 6.
Okay, let me, right, I'm going to talk about 14 for a few minutes and then I'll go straight to 6 after that, okay? So what we have here, I'm not sure I'm on the right page, is can you see that there's another question? So there's actually two, where the data is given and you have to get the mean and standard deviation, just like the one we did. And all of this stuff kind of follows. It's almost like it's the same question, isn't it? But with different numbers. So we believe it's 6. Once I get to 6, you can verify that that's it in case it's 5 or 7. This one here, right. Right, so what we're being asked here is to find the p-value. And the only thing they're telling us is 11 degrees of freedom in the t, right? So when I click on use salt, it looks like this, right? Now, can you see that the numbers are 11 degrees of freedom and 2.99? Let's see how that works. Make it a t distribution. 11 degrees of freedom. And the number is 2.99. When it is positive, you're wanting, for positive t-scores, you want the guy to the right. For negative t-scores, you want the guy to the left. So this was positive, so I want the guy to the right. And the number I want was 2.99. So I just go here and I type in 2.99. And this hidden number is the p-value. So 0.00615. So somewhere in this list, there is an interval that contains 0.006. 0.006 is there. So after all that hard work, 0.006, it's this one I just did. This is a right tail test. 0.006. So it's that one. Now, if I return, I'm now going to do a two-tailed. I just did a one-tailed, right? A right-tailed. Now I'm going to do a two-tailed. So hit this guy. It's still going to be a t-distribution. I'm going to have to shrink this down so we can see a little bit more. It's going to have 11 degrees of freedom. And it's going to be two-tailed, both tails. And the number is 2.99. You see in a two-tail, you tell the 9 in both sides, right? The 2.99 and the negative. And this fella, 0.0123 is the answer. So I want 0.0123, I think it was. Yeah, 0.01, 0.0123. And it'd be that one. Okay, did that answer your question?
Yeah, I just didn't know that we could switch it to that t-distribution on the chart. It's more what my question was leading to, but thank you.
Okay. I think there's only one question like that. I don't think there's a lot. If there is, there's maybe one more. That's all. Okay, let's just get this section finished. That's my goal. And then we'll be ready to start a new section next day. I misspoke when I said there's only a few. Actually, there's a lot where you have to get them in. So here is a story about, I don't like snow avalanches. Oh, that's interesting. Question 16. A national newspaper reported that the state with the longest average lifespan is Hawaii. So if you want to live a long time, go to Hawaii. And 73 years, that's not actually that good. A random sample of 20 obituary notices in Honolulu advertising gave this, John Smith died at 83, blah, blah, right? And we need to get the two numbers, the mean and standard deviation. So if I click on this, and I go descriptive statistics, there is your mean, 71.4, and right next door to it is your standard deviation, a 20.65, roughly. So pretty much just hit salt and read off the numbers that you see to 2 decimal places. We're good. And the significance level in this story is 5%. And we're looking for that the population line is less than 73. So less than 73 makes it that one, right? And the usual answer, because they're all the same, that one. And the rest is going to come from salt again. So I'm going to hit salt. And inferential statistics. And we got all the good stuff. And, oh, I forgot the question. And the question is it less than 73? $73, is it less? And the t that came out of it was a negative 0.34, and the p-value, these two numbers at the end here, is 0.366. How does that work? Well, you type in the t statistic, which is negative 0.34. And one of these guys is a 0.366, and it's a less than 0.366, so I'm assuming it's that one. And that is not statistically significant. And when it's not, you always pick the we fail to reject choice rather than the reject choice, which is the 1, 2, and not sufficient evidence. Are we comfortable with this question? What we've proved here is that the average life expectancy could be less than 75. We just don't know. Right? There's no evidence to prove it. Tree ring data, not really interested. And let's do the tree ring for the last one. That'd be a good question to finish on. Tree ring data from an archaeological excavation site is used in conjunction with other chronological evidence to estimate the occupation dates of prehistoric Indian ruins. So they collect evidence and they might say this particular native community was living here for 200 years or maybe only 20 years, right? Whatever it may be. And here is when they were doing it. They thought that this particular pueblo was being used around about 1298. Here is the data that tree rings came out with, different pieces of wood tree line, and we got this. So we're going to use salt to get the mean and standard deviation. Here's the data. 1268, I'll move it out of the way. 1268, the standard deviation for that sample was 37.2, oh, 1 decimal place. So 37.3. Significance level is 1%. Now, what do they want us to show this time? Does this information indicate that the population from the tree area is different from the other number? Right, so is it different? Is that one, right? Not the same as equals. And that's the standard answer. Now I need to get my T and my P, and we are done. So hit this again. Go over here, inferential statistics. And Is there enough evidence to show? We've got to read the question again. It's not 1298. Okay, gotcha. So 1298, and we're saying, is it not equal to it? And there's my t value, and 0.03 for the p value. There's the t value. I'm just going to round it to 3 decimal places because that's what they asked for. And although you can't see it, the p value was 0.03 and 0.03 is there. And since it's a two-tailed, you pick that one. Is this significant? Let's check it. Is 0.03 less than that one? Answer is no. So it's not statistically significant. And we fail to reject. Insufficient evidence. Whew. Perfect timing.